Hey folks, just going into the screen share. I hope I'm audible. Let's just check everything before we go in. Okay, seems everything is good. Sorry for a couple of minutes delay for us to join. We had a small hiccup here. Hope we should not have that. So a couple of quick announcements. So let me just put you here. So the first announcement is that today we have 30 questions, right? We have 30 questions. Actually, some of these questions are hard by design, right? So we intentionally, to be honest, some of these questions even took us quite a lot of time to solve. So some of these questions are hard without doubt, and some of them are okay. But we intentionally gave a few hard questions to prepare you better for the original GATE exam, right? Because GATE exam sometimes can be easy, sometimes it can be hard, right? Sometimes it can be fairly hard. For example, I still remember when I wrote GATE in 2006, it's one of the hardest papers that I've come across. I think even 2004 was hard, right? Even in the recent years, the harder papers have been fewer. It's mostly easy or medium that we are often seeing. But we wanted to give a few hard questions just for you to get a flavor of what hard questions would look like. And today, because we have a 90-minute session, we may not be able to finish all of the 30 questions. So we will go in the order, right? In the random order that I get questions in, and we'll try to solve as many as possible. For the rest of the questions that we cannot solve, we will send you detailed answers. We will send you detailed answers, right? We will send you detailed answers to all of our students. And if there is any question that you're not sure of or that you did not understand the answer for, do revert back to us. Please revert back to us if you have not understood a solution. We will certainly explain it in more detail and get back to you, right? So 30 questions I don't think is possible in 90 minutes, especially given that there are some hard questions which require more detailed explanation, right? So that's one. Second thing is we want to finish the whole of data structures and algorithms by the end of March, right? See, we started this on February 15th. We started slow, but we think hopefully by end of March, maybe in the last week of March sometime, we should finish whole of data structures and algorithms and move to the next subject, right? That's our objective and goal. So let's try to, of course, sometimes to reach this deadline, remember, we want to finish the whole course content for you by late August, early September, right? Sometime in early or even mid-September, we want to finish, at least for the first batch that we have, we want to finish everything by late August to mid-September, all the subjects once, so that you have a few months of preparation time. And to achieve that, we should constantly push ourselves. So from now till the end of March, we might push you a little to finish the content faster and also to do assignments. So if we push you, it is all for the final objective that if we can finish everything by mid-September, late August, maybe mid-September or so, we will have lots of time for practice. And our first batch of students who took the initiative to join early should certainly get more time, especially for problem solving, hence improving their chances, right? So we'll give you, again, we'll share the schedule for you for the next Wednesday, right? And all the practice questions by tomorrow morning, worst case tomorrow afternoon, right? But we'll push you a little. Just wanted to make that clear before we go into the question answer session, right? So Naveen, you're looking at the chat, right? So let's go step by step, okay? So this is my first question here. By the way, we will not solve this question because there are a couple of concepts here that require. So for example, this is a question about external merge sort. It's a very good question. To be honest, this is a very good question. One of our teammates actually set up this question by actually looking at University of Berkeley's. So he has actually taken this question from University of Berkeley lecture notes and assignments. It's a very good question, but unfortunately, this requires considerable amount of knowledge about, so because look at this, it asks about, it says I have 105 pages. Now, what is a page? You have to know concepts in operating systems, right? You have to know concepts in operating systems like paging to solve this problem better. You have to know concepts like disk IO, or what actually happens when you read something from your disk to your RAM. And you have to know that disk IO is much slower than reading from RAM, all of those other things. So this requires, and you have to understand about buffers, how buffers work, right? So this question requires some knowledge of operating systems like paging and disk IO. and hence we will certainly solve this problem. We've actually moved this problem into our operating system content. So we will certainly solve this once we learn about paging and disk IO in operating system. It's a very good problem. Unfortunately, to explain this problem right now might take us half an hour, because I have to explain a lot of concepts in operating systems, and I don't want to jump to paging without explaining the basics of OS, right? So this question, unfortunately, the very first question, but this is a very good question. This is terrific, actually. I loved solving this question, but then I realized that there are lots of pieces here, other concepts that you need, right? So let's jump to the second question here. Oh, this is a simple question, actually. So this question is basically saying that, again, I've solved all of these questions beforehand, or at least tried to solve as many as possible beforehand, so that I don't make silly mistakes. A CPU can perform 10 power 8 operations a second. Okay, you are implementing an algorithm that is order of n square log n base 2, right, to solve the problem. You want to demonstrate the algorithm to your boss or your manager or your professor and ensure that the program runs within 1 second on all demos. Among the following values of n, which is the largest safe value for the demo? Okay, so basically your CPU can run 10 power 8 operations. So imagine if my input is 7,500, which means n is equal to 7,500. When n equals to 7,500, I want to compute order of n square log n base 2, right? Which is, so this I'm ignoring the constant factor here. When I'm writing order, I'm just ignoring the constant factor for a while. Now when I replace this n into this 7,500 square plus log 7,500, right? Of course, for this I can use my calculator here, right? Even in the gate exam, you get this calculator. So you have 7,500, sorry, you get 7,500 into 7,500. I'm just showing you how to use the calculator just in case, which is, what did you get here? You got 56250000. And in this calculator, you also have log x, right? Base 2. So you have 7,500. Just compute the log x of this, you get 12.87, right? So to this you want to multiply. So this you want to multiply 5625 4 zeros, right? So what did you get here? Okay, come on. Okay, so I think because I'm using a tablet interface to write this, let me write it more carefully. So 7,500 log base 2. Okay, so let me just write down this number also here, 12.87267, right? So now I want to multiply this with, okay, okay, got it. Now I want to multiply this with 56250000. One more zero here. Okay, so this is what I get, right? What did I get here? I got roughly, so for 7,500 I got 7.24 into 10 power 8. Look at this, 332 10 power 8, right? So you can use the calculator like this even in the actual exam itself. I just want to show you how to use this calculator here, right? So if I apply n equals to 7,500, use the calculator and compute n square log n, I would get 7.24 into 10 power 8, as we just saw, roughly. So, and we know that the CPU can perform 10 power 8 operations a second, so which means this will take 7.24 seconds, assuming the constant in the big O notation is equal to 1. That's the assumption we are making, okay? For 5,000, again, if you just repeat the same thing, you get 3.07 seconds, or you would get 3.07 into 10 power 8. That's the same exercise we have to repeat. For 2,000, you will get 0.44 seconds. For 3,000, you will get 1.04 seconds. And the question asked here is, what is the largest safe value? And you want to run the demo within 1 second. Obviously, even if you pick 3,000, you'll take more than a second. And you want to be on the safer side, right? So picking 2,000, which is the smallest of all the 4, is the safest bet, right? This type of question is going to be calculator heavy. Okay, because you have to literally replace everything. So it is important for you to learn to use the scientific calculator well in advance, right? Otherwise, you'll fumble at the last minute. You could get some questions like this in the actual gate questions itself. Okay, so let's go to the third question now. the number of swaps or swaps actually needed to sort this array in ascending order using bubble sort. Very good question actually. So let's look at this. So, okay, I don't have to write the whole array itself. So in bubble sort, one of the key properties of bubble sort itself is you will only swap those elements. For example, look at all the swappings that 8 will go through. 8 will be swapped only by those numbers. Remember, we are using bubble sort. We discussed bubble sort and how it works in lots of detail in the course. One of the properties that you might have observed while doing bubble sort is 8 will only be swapped with all the numbers to the right of it, which are less than 8. So 8 would be swapped with what are all the numbers to the right of 8, which are smaller than 8, 7 and 5, right? So 8 would, so when you actually run bubble sort on this whole thing, 8 would get swapped only with 7 and 5, which means there are two numbers that 8 would get swapped with in the actual bubble sort, right? Similarly for 22, what all numbers are there to the right of 22 that are smaller than 22, right? You have 7, 9, 19, 5, and 13. You have 5 numbers to the right of 22 that are smaller than 22. So 22 would get swapped with all of them, right? Because see, look at this. At the end of the day, 22 has to jump over these numbers, right? At the end of the day, 22 has to jump over those numbers and move to the right, in bubble sort. That's what it has to do, right? So to do that, these things need to get swapped. Similarly, if you do it with 7, there is only 5, which is smaller than 7, which is on its right side. Just a quick water break. Just give me 5 seconds. Okay, so here 7, there is only one number to the right of 7, which is smaller than 7, which is 5. Now let's go to 9, right? So 9, there is only one number again, which is 5, which is to the right of it, which is again less than 9. Similarly for 31, look at this, for 31, you have 19, 5, and 13. You have 3 numbers. Okay, you have 3 numbers here. For 19, okay, let's look at, for 19, you have 5 and 13, which are smaller than 19, which are to the right side of it. Right? So for 19, you have 2. For 5, you have nothing, right? There is only 13 to the right of it, and 13 is larger than 5. And for 13, there are no numbers to the right of it, right? So now if I sum up these numbers, 2 plus 5 plus 1 plus 5 plus 13 plus 2, what you get is 14, right? Just sum it up, you'll get 14. So 14 is the number of swaps that are needed using bubble sort to sort these numbers, right? So this is a very good question because it helps you understand bubble sort in a deeper sense of what's happening, right? Okay. So let's go to the 4th question. Okay, so let me go to the 4th question. Today we have zoomed in the screen a little because I think last time some students mentioned that the questions were not clear, so we zoomed in the screen a little bit today. Okay, the 4th question here is, consider a sorted array A of n integers, right? Sorted array in ascending order, obviously, right? A0 to an-1, and the pseudocode for bubble sort. So this is the pseudocode for bubble sort, right? So in this case, what's happening? This is like a brute force-ish bubble sort, right? If you think about it, this is not the bubble sort that we studied in the course. What we studied is a more optimal implementation of bubble sort, right? So here, what are you doing? You're going from j1 to n-1, I from 0 to n-1 minus j. And if this is greater than this, basically it's checking ith element and I plus 1th element, and it would keep swapping. Now the question here is, what is the maximum number of times swap is called when bubble sort is performed on the above array of integers? Very good question. It's actually a tricky question, right? Because look at all the facts we are given. We are given an array in ascending order, which is already sorted, right? Now, the time complexity of this algorithm is obviously order of n square, right? Because you have this twin loop. Look at this twin loop that you have. This goes from 1 to n-1, and this goes from 0 to n-1 minus j. So obviously, the moment you see this, the time complexity is certainly theta of n square. And you might get tempted to put this or this as the answer, but they are not the answer. Because the question says, what is the maximum number of times swap is called? If your array is already in sorting order, there is no swapping needed, no? Your array is already in sorted order, so there is no swap needed. That's why it's a tricky question. You need 0 swaps for this question. Right? So the right answer here is 0 because the array is already in ascending order and you don't require any more swaps for the bubble sort. Right? But the time complexity is certainly order of n square, without doubt, because you have this interesting twin loop here. Right? Again, whenever you have twin loop, you need not have order of n square. You have to be careful to look at twin loops. We have seen some examples in the previous practice problems. Okay, so this is a good and tricky question actually. Okay, so let's go to the 5th question now. Okay, so this is a good question again. You have to sort a list L consisting of a sorted list followed by few random elements. So you have this where there is a bunch of sorted. So this part of the array is already sorted, right? And you have a bunch of random elements here, right? You have a bunch of random elements here, a few random elements, right? There are a few random elements here, not too many. Which of the following sorting method would be best suitable for this task? Okay, first thing you have to realize is, I would say insertion sort without even blinking an eye. Because what do we do in insertion sort? At insertion sort, and at any iteration I, right, we have a bunch of values which are already sorted. We take the next element and we try to insert this into this sorted array in its appropriate position. That's what we do in insertion sort, right? That's the intuitive understanding of insertion sort. So if you already have a large part of your array sorted and only a few elements that are unsorted, obviously insertion sort is a good idea, right? Obviously, this makes like obvious sense. Why not selection sort? Why not selection sort? Because in selection sort, we are selecting the smallest element and putting it at the start, or the largest element and putting it at the end. Which means this whole structure, you're not leveraging the structure that you have. That a large part of your array is already sorted. You're not leveraging the structure. Why not bubble sort? Right? In bubble sort, because I have a few random elements, if these random elements are smaller than all the elements in my sorted array, I'll have to make many swaps like this. Because we saw that in the previous question, right? If these elements, look at this, if these elements are all smaller, if all these elements are smaller than my sorted array, which could be the case, then there are lots of swaps needed. So bubble sort will never be the optimal choice, and we're not leveraging the structure that a large part of our array is sorted. And there are only a few elements that are unsorted. So insertion sort obviously makes a lot of logical sense here, right? So next is the 6th question. This is straightforward. We have solved tons of problems like this till now, right? So actually, we have solved very similar problems earlier also. So I'll quickly go over this. In the previous practice problems, we've already solved this, right? So look at this. So this is a constant, right? This number is large, but it's nonetheless constant because there is no n here, right? So this is obviously the slowest growing. So either this is the answer or this is the answer. This cannot be the answer and this cannot be the answer. Because what do we want? We want to rank these functions in non-decreasing order, right? Now let's look at the rest of them, right? You have, so after this, so the big question here is, see, because one of these two can be the answer, you have to compare this versus this. This is basically a polynomial in n. This is basically order of n, right? This is order of log n square. What is the order of log n square? So log n square. What is log n square? It's nothing but 2 log n, no? Right? Log n square is nothing but 2 log n. And this is nothing but order of log n. Right? And this is order of n and this is order of log n. Right? Obviously, order of log n grows slower than order of n. So this cannot be the answer. So you're only left with this option. Even by checking a 2, 3 of them, you've already converged to the answer. But of course, you can see here also that this is basically a log. This is basically a logarithmic complexity. This is basically linear. This is quadratic because there is n square. However, the small the constant is, I still have n square. This is cubic, n power 3. And this is exponential, right? Because you have, see, this 3 by 2, what you have 3 by 2 here is greater than 1, right? This is like c power n. We've already seen the asymptotic order of functions. We have solved tons of problems. So 2 is the right option here, right? Very simple question, nothing very hard here. Again, we have solved tons of problems like this. This should not come as a surprise anymore, right? So next question is 7, right? So define the recursion depth of Quicksort to be the maximum number of successive recursive calls before it hits the base case. Okay, very good. Equivalently, so this is basically the recursive Quicksort implementation, right? Equivalently, the number of the last level of corresponding recursion tree. Okay, so we know the recursion tree, we know this concept. Note that the recursion depth is a random variable. Yes. Why is it so? Because your recursion depth will depend on how your pivot. See what happens here in Quicksort. You have a pivot. All these elements are less than equal to pivot, and all these elements are greater than equal to pivot. Right? And if there are k elements here, there will be n minus k minus 1 elements here. Right? And your pivot could split it in any way. Right? So what is the minimum possible and the maximum possible recursion depth of Quicksort? We know this. We have already discussed this, right? When we discussed Quicksort, we actually drew the Quicksort algorithm and we said that what is the best case of Quicksort, right? The best case of Quicksort is 2tn by 2 plus cn. This is if you write the recurrence equation of Quicksort, this is the best case, right? This is the best case of Quicksort, right? So if I draw the recurrence tree for this, what is the depth of this recurrence tree? It will be theta of log n, right? Because you have 2tn by 2. Because of this, if you draw the recurrence tree, right, you get a depth. Your depth will be equal to theta of log n. And what is the worst case for Quicksort? Tn equals to tn minus 1 plus constant time. Basically, if you have a very skewed thing, right, that your pivot is here, right? Your pivot, let's assume it's already in sorted order, right? Then your pivot will always be here, and your array is going to get broken down. Your k basically becomes 0. Basically, that's what, if it happens every time, then you get the worst case. In this case, what is the recursion tree depth? It is theta of n, right? Because a problem of size n is getting broken down into a problem of size n minus 1, and so on and so forth. We have seen these recurrences a lot in earlier practice there. That's why I'm not going deep into this right now, because we have solved almost like 50 problems on similar stuff, right? So, okay, so what is the answer here? What is the maximum and the minimum possible recursion depth? The minimum is theta of log n. The maximum is theta n, right? That's the right answer. If you don't read this minimum and maximum correctly, you could also write the answer as B. So be careful when you read it. Read the order. Minimum and maximum respectively will be theta of log n and theta of n, right? Again, very simple, straightforward question. Looks tricky at the surface, but it's actually a very simple thing. Okay, so next comes this question. An array of n integers is arranged in a random sequence. Okay, just give me a sec, just a quick water break. Yeah, I need to keep taking these water breaks because I have a terrible cold and just want to make sure that I don't sneeze or do anything crazy in the live session. So just excuse me, I have a slightly broken throat, so I need to take more water today. An array A contains n integers arranged in a random sequence. We want to check if any value is duplicated in the sequence. Okay, very good question. So you have an array of n integers in a random sequence. So the sequence is random. You have n integers. We want to check if any value is duplicate in the sequence. Which of the following would be the most efficient algorithm? Let's check one by one. For every pair I comma j, check if ai is equal to aj. So this will be a theta of n square time complexity, right? Because you're checking every pair of numbers. Sort the array using insertion sort. When inserting each element into the sorted prefix, check if there is a value already equal to the prefix. Okay, this is interesting. But we know that the insertion sort, right? The worst case could be order of n square. In the worst case, I might have to make order of n square comparisons even here, right? What is the third option? Sort the array using merge sort. This I can perform in order of n log n. Scan the sorted array from beginning to end, looking for adjacent equal elements. So my initial sorting will take order of n log n. Then to scan it from beginning to end, looking for adjacent equal elements will take order of n. So this whole thing is still order of n log n, right? What is the fourth option? So this seems to be a possible candidate, but let's read the fourth option also. Sort the array using Quicksort. Use binary search on the sorted array to find duplicates. Again, we will discuss binary search in one of the later chapters that I think we will allocate today or tomorrow, or for Wednesday or for next Saturday. Okay, but don't worry. Quicksort in the worst case could be order of n square, right? So obviously, forget about the binary search part. Just sorting the array using Quicksort could be order of n square in the worst case. So the best algorithm here amongst the 4 is option 3 or C, basically, right? So straightforward question. If you know basic sorting algorithms, this should be straightforward. Okay, this looks scary, but let's see. Okay, so you're given a sequence of n elements to sort. The input sequence consists of n by k sequences, each containing k elements. Okay, so you're given an array, right? Or you're given a sequence where you have n by k elements, right? Sorry, you have k elements. Sorry, you have k elements here. You have k elements in the first sequence. You have k elements in the second sequence. You have k elements in the third sequence, so on and so forth. And the total number of elements are n here. So you have n by k such sequences, n by k subsequences. Okay, the word used here is n by k subsequences. Okay, makes sense. The elements in each subsequence are smaller than the elements in the succeeding subsequence and larger than the elements in the preceding subsequence. Okay, that's a very good point. So what does that mean? It means all the elements in this subsequence are going to be less than equal to elements in this subsequence, which are going to be less than equal to elements in these subsequence, which are going to be less than equal to elements in the next subsequence, and so on and so forth. That's what the next line says. Thus, all that is needed to sort the whole sequence of length n is to sort the k elements in each of the n by k subsequences, obviously. Because I know, because imagine if I can sort this, 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 because these are not sorted, nothing is told about them. They could be in any order, right? So if I can sort each of these n by k subsequences, I would immediately get a fully sorted array, because I know from the problem definition here, I know that all these elements are less than equal to these elements, right? Which are less than equal to these elements, and so on and so forth, right? Because of that property, can I somehow leverage that? Okay. Now the question is the lower bound on the number of comparisons needed to solve this variant of the sorting problem. Very good. This is straightforward. So imagine I have to sort this. To sort this, how much time would it take? K log k, right? Because the number of comparisons that I need will be k log k, right? Using any major algorithm, right? Because we know that the number of comparisons to sort n numbers using any comparison sort is n log n. So this would also take k log k, so on and so forth. So I'll take k log k, and I have n by k such sequences, right? So this would take k log k, this would take k log k, so on and so forth. So the total time, k could get cancelled. The total time will be n log k, right? So the answer here is n log k. This is the lower bound, obviously. This is the lower bound on all of the comparisons. Makes a lot of sense, right? Straightforward question. C is the right choice here. Okay, so let's go to the 10th question here. Okay. So the 10th question talks about three-way merge sort, right? So we have a three-way merge sort, and suppose that instead of dividing in half at each step of merge sort, right? Instead of dividing in each step of merge sort, you divide into thirds. Okay, you divide into thirds. Okay, sort each third, and finally combine all of them in a three-way merge subroutine. What is the overall asymptotic running time of the algorithm? Hint, note that merge step can be implemented in theta of n time. They're already telling this. So what do you have? You have Tn equals to 3Tn by 3 plus they're saying that merge can be implemented in order of n. Okay, if they have not given that, the problem would have been more fun, but they've given it. So life is simple. So if you have this, of course, this is like straightforward reconciliation, right? I mean, we have solved tons of these reconciliations like this. This you can trivially solve it and write it as an order of n log n. This is straightforward. Of course, this log will be base 3, but doesn't matter. When you're writing in big O notation, you don't have to specifically mention this. Not worry about it. So this is straightforward. Of course, I'm not solving the reconciliation here because it is straightforward. If you want it, let's do it, right? So you have n by 3, you have n by 3, n by 3, right? Again, you have n by 3, n by 3, n by 3. So we have seen a lot of problems like this, right? The depth of this tree will be log n base 3, right? And in each case, you have Cn. In each case, you will get Cn, right? So if you sum up everything, you'll get Cn into log n base 3, which will be order of n log n. So the moment you see something like this, you can either apply Master's theorem type of cases, or you can draw the reconciliation and be able to quickly answer them. Okay, I wish this question did not give this, that much can be implemented in theta of n. Then it would have been fun, but since it's given, the question becomes easier. Okay, so let's go to the next question here. Okay. So, okay, so let's go step by step here, right? So the question here is, you have a function fun with two integers a and b. If a percentile b equals to 0, return b. So this is basically the modulo operator in C, right? This is basically the reminder when you divide a with b. Else, return function b comma a percentage b. Okay. So what will be the output if you do this? I think this was a question that I answered in GATE myself in 2007. I think, because I remember this question very vividly. Okay, so we have this question where f 11 comma 3, right? So the moment you have 11 comma 3, what is 11 percentile 3? 11 percentile 3, which means 3 3s are 9, so the remainder is 2, right? So what would this happen? So this condition is not met, so I'll call this function now. So this will call f of b. So this is a, this is b, this is a percentage b, this is a percent b. So what would I call? fb. What is b? B is 3, a percent b is 2, right? Now what would I compute? 3 percentile 2. So this is a, this is b. A percentile, 3 percentile 2. 2 ones are 2 and remainder is 1, right? Now what would this call? This would call f of b. B is 2 and a percentile b, which is 1. Now when this is called, I will compute 2 percentile 1. This is obviously 0. When this is 0, what happens? If a percentile b equals to 0, return b, right? What is b? B is 1. So this function will return 1 here, right? This function will again return 1 here, right? So what is the whole overall output of this function? This function will also output 1. So the final output is 1 here, right? You just have to understand how recurrence works, or how, sorry, not recurrence, how recursion works here. It's a straightforward problem, nothing very complex here. You just have to be careful not to mess up a, b, and a percentile b. That's it. Okay, sounds good. So let's go to the 12th problem. Okay. So let the numbers 794, 332, 561, 342, 200, 607, and 893 be sorted using Radix sort. Okay, we have seen what Radix sort is anyway. What will be the 6th number in the sequence of numbers after sorting the second digit? Okay, so let's write down. Okay, so what are the numbers that we have? We have 794. This we need to write down carefully, right? So 561, 342. This is a time-taking question, but we have to be careful. 200, 607, 893. Okay, so these are the numbers I have. First, let's solve the first digit. That's how Radix sort works, right? Now, while sorting it, of course, 0 is the smallest, so I'll place 200 at the first. Then, is there a 1 here? Yes, I have 561, so let's place 561. Sorry, let's place 561. Do I have 2? I have 2 elements that are ending in 2. Remember that Radix sort is a stable sorting algorithm. This is a very, very important property. I think this whole question was designed to test whether you know that Radix sort is stable or not, which means 332 will come before 342. That's very, very important, right? This order will remain the same. The element that comes before in the original list will come before even while sorting, if the 2 elements are the same. That's extremely important. Okay, then you have 893. 3 is done. Then you have 794. Then you have 607, right? So first digit is sorted. Now let's sort the second digit. Okay, while sorting the second digit, again it will be stable. What is the smallest? 0. So we have 200. Next to the second digit, what is the smallest? 607 is also there, but 200 is before 607 in this order. So the same order will be maintained here because the second digits are the same here, right? Very important because of the stable sort property. Next, what is the smallest? Next, you have 332, right? Because you have 3 here, right? Then you have 342 because you have 4 after that. Like after 4, what do you have? You have 561, right? You have 561. So 6 is also taken care of. Then you have 2 numbers with 9, right? You have 2 numbers with 9. So this comes before this. So 893, followed by 794, because 893 is before 794 in this list. Because it's a stable sort, the order is maintained. Now comes the question. What will be the sixth number in the sequence after sorting the second digit? So first number, second number, third number, fourth, fifth, sixth number. 893 is the answer. If you messed up the stable property or the stability of Radix sort, you would have messed up the whole solution itself. This whole question was designed to test if you know stable sort or not. If you know that, sorry, Radix sort or counting sorts are stable sorts or not. Okay, that's all this question is all about. Okay, so now let's go to the 13th question. I hope anyway, if anybody has a question, do chat, do put in the chat window. We'll try to answer as many as possible in the limited time that we have. Just a quick water break. Just give me a sec. Okay, sounds good. So let's go to the 13th question here. Consider the following function that we have here, and int f in 10. Okay, this is a C function. If n equals to 0, return 1. Otherwise, return fn minus 1 minus n plus fn minus 2 plus 2. Okay, so what is the output if f5 is called? Okay, this is going to be time taking. Let's start with f1, because we know f5 will anyway call f1 eventually, so it's better to start from f1 onwards. We know f0 equals to 1. Look at this. If n equals to 0, return 1. We know that. What about f1? For f1, what do you get? You get f n minus 1, which is f0, minus n. N itself is 1, plus, again, f0, plus 2. And what is f1? F1 is 1 minus 1, plus 1 plus 2. These two get cancelled, so f1 equals to 3. Now what about f2? Let's go to f2. f2 equals to f1 minus 2 plus f1 plus 2. So minus 2 plus 2 would get cancelled. f1 is 3. f1 is 3 here, right? f1 plus f1, so this will be 6. Similarly, f3. You can actually do the same thing again and again. Just in the interest of time, I'm not showing it here. f3 will be 11. I've just written it in my notes. f4 will be 20. And f5, let's do f5 since that's the question asked, right? f5 is going to be f4 minus 5 plus f4 plus 2. What is f4? This is 20. This is 20. So 20 plus 20 is going to be 40, right? 40 minus 5 plus 2, right? So 40 minus 5 plus 2, which is 40 minus 3. That will be 37, right? So this whole thing is time taking. This whole thing will take time. You have to be careful. You cannot mess up this reconciliation or this recursive call here. But if you're careful, you can trivially solve this. These types of problems are not hard. They are just time taking, and you will fall into silly mistake traps. Okay, that's what you have to be careful about for problems like this. Okay, sounds good. So the next one, which of the following cannot be an intermediate sequence if you apply Quicksort on these numbers? Okay, this is a good one actually. This took some time to solve, not because it is hard, but because it is time taking to solve. Okay, so let's start with this. Assume the pivot is always the first element. This is very important. Without this, I'll not be able to solve this problem. And the question says which of them cannot be the intermediate sequence. So we have to literally test the whole thing. So I start with 9, 8, 7, 6, 5, 4, 3, 2, 1. This is my first pivot, right? And now I have to place my pivot somewhere. Remember that all these elements are smaller than pivot, right? All these elements are smaller than pivot. So at the end of first iteration, what will happen is 1 and 9 would get swapped, right? If you recall how Quicksort actually works, I have these two pointers I and j, right? So at the end of it, what happens to me is I would get, at the end of first iteration, I would get 6, 5, 4, 3, 2, and 9. So 9 is already sorted now, because look at this. This is a sorted array. What you're given here is a sorted array in descending order. So now this problem, because this is your pivot, there are no elements to the right of the pivot. The only unsorted array left is this part. This is the unsorted array, right? This is your pivot. So this is basically breaking a problem of size n into problem of size n minus 1 plus 0, right? So this is basically that worst case of Quicksort. Okay, fine. So this is after first iteration. Is this there somewhere? 18765. Yes. So this is an intermediate step. The question here asks cannot be an intermediate step. So one cannot be the answer. Okay. So now what happens in the second iteration? Let's see. So one will be your pivot now. Okay. Now one thing you have to notice is all these elements are greater than one. Right? So what will happen? Because you're solving this on this sub array, you're doing quicksort. So what would you get? One will remain in its location, right? One will remain there. Nothing will happen to one, right? You will be left with 9 here. So 1 and 9 are trivially sorted. This is the sub array which is not yet sorted, right? Because look at this. The sub array that we had to sort was this whole thing, and we picked up the smallest element. Again, this is the worst case of quicksort till now. Okay, only these underlined elements are still to be sorted. Rest 1 and 9 are already sorted. Next, so is this there somewhere? This is not there anywhere here, right? Okay. So third iteration. Now this is my pivot. Now. Now I will try to move all the elements in such a way that, okay, by the way, 8 is the largest element here. Okay, all these elements are less than 8. So what will happen? 8 and 2 would get swapped. So what will happen here? 1 will remain here. 9 will remain here. Your 8 and 2 would get swapped, right? So 2 will come to the first, 7, 6, 5, 4, 3, and 8. So 8 is already sorted now, okay? Because there is no sub array to the right of 8 that I have to worry about. This is the unsorted array now. Is this there somewhere? 1, 2, 7, 6, 5, 4, 3. Yes. But this also cannot be an answer. Okay, now 2 will become the pivot. Now the interesting thing is 2 is the smallest element again. Right? 2 is the smallest element, which means 2 will remain here and it will get sorted. Right? 2 will remain there and 2 will get sorted. Now, what are my unsorted elements? These are my unsorted elements. Okay. So fourth iteration also the same thing remains here. In the fifth iteration, what happens? Now my 7 is the largest element here. Right? My 7 here is the largest element, which means my 3 and 7 would get swapped now. Right? So what will happen? 1 is sorted, 2 is sorted, my 3 will be here. 6, 5, 4, my 7 here, 7 is already sorted. 8 and 9 are anyway sorted, right? Because 7 is the largest element here. When you run quicksort, what do I get? 1, 2, 3, 6, 5. Okay, so this also cannot be the answer. Since all the 3 cannot be the answer, this has to be the answer. But anyway, since we are here, let's finish this off. The next pivot will be 3, right? And now what will happen? So all the elements smaller than 3 will be here. So 4 will come here. Anyway, we have solved it. This is the answer. Of course, you can keep going on 2 more steps and you will get a sorted array, right? Obviously. So since all these 3 are eliminated, only 1 is left with, and you will not get this as the intermediate array, right? Okay, sounds good. Very simple. So again, the question here is intermediate sequence, not the final sequence. Remember, this is the final sequence. This is the final sequence, obviously, because you want to sort the array in the first place. So many people might get confused and say this cannot be the answer, right? Because this is the final array, right? But this is an intermediate array. Look at this, 1, 2, 3. Oh, sorry. This is not the final array. I'm sorry. I got confused because 5 and 4 are, 5 and 4 are swapped. This is not a sorted array. I'm sorry, my mistake. Sorry, these 5 and 4 are not in their positions. Anyway, so since we have eliminated A, B, C, D is the answer. You can check it also. Just in the interest of time, I'm moving forward. Okay. So let's go to the 15th problem. Okay, I think I answered this question anyway. Okay, so which of the following statements about quicksort is correct? Okay, average running, is incorrect. I'm sorry, is incorrect, not correct. Okay, see, these are the mistakes. This is what costs you dearly. Okay, in my own experience, I think this is what cost me a good AR1. I'm sure I messed up some questions like this because in 2007 the question paper was trivial, right? I got 2 because I think I messed up at least 1 question because of this. Anyway, you got to be careful. Don't repeat the mistakes that I or others like me have done. Okay, average runtime is order of n log n. This is certainly right, so this cannot be incorrect. The best case occurs when pivot partitions the set of numbers to be sorted into 2 equal size subsets. Obviously, that's the best case, so this cannot be incorrect. The worst case occurs when the pivot partitions the set of numbers to be sorted into 2 equal size subarrays. Obviously not. This statement is incorrect, which means this option is right. Let's also read the 4th option. The worst case occurs when the smallest element is selected from the item to be sorted as a pivot? Obviously not. So the worst case always occurs when the smallest element is selected from the items to be sorted as pivot. The worst case occurs. This also sounds right? Oh, this is right, yeah. So this is right. So the question is, which statement is incorrect? Okay. So these three statements are correct. There is only option C which is incorrect. Okay. So option C is the right answer. Okay. So again, these incorrects can confuse you like crazy. Trust me. I have done enough of those mistakes myself. Okay. So this is a slightly tricky question. Okay. Let's go step by step. A CPU can process 10 power 8 operations per second. Suppose you have to sort an array with 10 power 6 elements. Which of the following is true? Okay. So it talks about selection sort will take more than 2.5 hours, while merge sort will take less than 1 second. Okay, let's see. Insertion sort will take more than 2.5 hours, while quicksort will take less than 1 second. Or will always take. Okay. See, there is this word always take more than this. Okay. Will always take. Always is the keyword here. Insertion sort could take. This looks like a grammar question to me. Insertion sort could take more than 2.5 hours, while merge sort will take less than 1 second. Okay, selection sort could take more than 2.5 hours, while quicksort could take less than 1 second. Let's look at it, right? So obviously we know merge sort merge sort has n log n, right? If my n is 10 power 6, what is n log n? 10 power 6 log 10 power 6, right? So this is roughly 10 power 6 into 6 into log 10. Log 10 is basically 3 point something, right? So this is roughly, if you think about it, this is 6 into 3 point something, 10 power 6, right? So let's approximate this to 20 into 10 power 6. Approximate. Certainly this is going to be less than 20 into this, right? Obviously. You can compute that using the scientific calculator if you want. Now, the fun part here is it takes 10 power 8 operations per second. This will certainly take less than 1 second. What about selection sort, insertion sort, and selection sort? They all are n square. Even quicksort is n square, right? If n equals to 10 power 6, what is n square? Here I'm ignoring the constant factor. Remember that I'm ignoring the constant factors here. Okay, I'm ignoring them just to make the math simple. So this will be 10 power 12. What is 10 power 12? 10 power 12 is 10 power 4 into 10 power 8, right? Which is 10 power 4 seconds. And what is 1 hour? 1 hour is 3,600 seconds, right? 1 hour is 3,600 seconds. So 2.5 hours is 3,600 into 2.5, right? That's roughly your 7,200 plus 1,800, right? So that's about 10K, right? That's about 10K. That's about 10 power 4. So this is 2.5 hours with a constant factor of 1. Remember, here the constant factor was 1. The constant factor could be more, right? Here, even if I have a constant factor of 5, I'm still good, right? So my constant, if it is 1, 2, 3, or 4, or 5, I'm good. So merge sort can actually solve this in under 1 second. So now let's look at it. So here also it says merge sort will take less than 1 second. Here also it says merge sort will take less than 1 second. So either option A or option C must be correct. But there is this tricky thing. Selection sort will always take more than 2.5 hours. No. There is a best case of selection sort, right? Right? If I take the best case of selection sort, it is not order of n square. So this will always is the incorrect. So this cannot be right. Insertion sort could take more than. Yes, it could take in the worst case. Because the worst case of insertion sort is order of n square. Right? So in the worst case, it could take. So the could and always. That's a tricky part here. So option C is the most sensible option. Because obviously quicksort will not take less than 1 second. Quicksort. So these two are incorrect. Because quicksort is also in the worst case order of n square. Right? So it's only merge sort that is guaranteed to be n log n, which means it still has a good possibility if my C is between 1 to 5 that I can solve this in under 1 second. And insertion sort could take more than 2.5 hours. Obviously, it could take more than 2.5 hours in the first case. It will always take is different from could take. That's why I said this is a grammar question. Okay, so you have to be careful because I got confused when I'm trying to solve this. So option C is the right option in this case. Okay, little tricky. You have to be careful, but you can solve it. Okay, so let's go to the 17th question. This is a good question, actually. I found an interesting trick to solve this. Of course, there are many ways of solving this. Okay. So T0 equals to 0, T1 equals to 1, and each of the following recurrences for n greater than equal to defines a function t on non-negative integers, obviously, as expected. Which of the following cannot be bounded by a polynomial function? What is a polynomial? N square, n cube, n power 4. All these are polynomials, right? Actually, you can solve each of these recurrence relations using extended master's theorem. You can actually solve it. But there's a faster way to solve this problem, which is, look at this. Okay, look at these 4 options, right? What does this look like? This is basically breaking a problem of size n into 3 problems of size n by 2, right? Which means you'll have some form of log n here. And of course, there is cn square here also. So you will eventually get something like n square log n type of stuff here, roughly of this type. Okay, worst case. Okay, of course, if you solve it exactly, you might get a slightly different term here. Of course, you can do extended master's theorem and get the exact term here, right? But the very fact that your problems are getting broken down into problems of size n by 2. Look at these 2 cases. Look at these 2 cases. Your problem of size n by 2 is getting broken. Problem of size n is getting broken into problem of size n by 2, problem of size n into n by 2, which means these both, and again, the constant term here is quadratic, right? This is quadratic and this is linear. So these both, if you actually, again, you can put in extended master theorem and get the answers here. But so actually, if you put in the extended master theorem, I think you would get order of theta of n square here. You can actually put in your a, b, c, all of that and get it. Okay. In the second case also, you'll get theta of n square, right? But if you don't put in also, by just looking at this breakage, you can answer this. I think the most interesting part is, let's look at these 2 cases. Okay. So this is breaking a problem of size n into problem of size n minus 1 plus n square. So if you think about it, n into n minus 1 and n square here. So this will be n minus 2 again, right? This will be n minus 1 square. So on and so forth up to 1. So what do you get? You get summation of I square with I going from 1 to n. Right? This is obviously a polynomial sum. This is a sum of polynomials, right? So this got to be polynomial. So this will also be polynomial. Again, you can solve this. You can solve it using extended master's theorem for decreasing functions, and you'll get theta of n cube. Okay, you can solve it. But I'm just saying, without even solving, if you don't recall master's theorem, you can use this logic internally and get this roughly. See, at the end of the day, you can only if it's polynomial or not. You don't require the exact functional form. Now, this is the fun part. So this is the only one left. But the intuition that you have, that you can get here is, you have a problem of size n, which is being broken up into 2 problems of size n minus 2, and some constant time 1 here. Now, this looks very similar, not exactly, but it looks similar to Fibonacci. What happens in Fibonacci? Tn becomes Tn minus 1 plus Tn minus 2, right? This is what your Fibonacci series looks like, right? Fibonacci series has an exponential time complexity. We have solved this in the course videos. This looks very similar to Fibonacci, where a problem of size n is broken down into 2 problems of size n by 2. Right? Again, this will be broken down into, sorry, not n by 2, n minus 2. This will be again n minus 4, n minus 4, n minus 4, n minus 4, so on and so forth. But this looks surprisingly very similar to Fibonacci. The only difference here is, instead of Tn by 2 and Tn minus 1, you have 2 times Tn minus 2. So this looks, the moment I saw this looked very close to Fibonacci, and I know Fibonacci is exponential. So this is the only option. Of course, you can eliminate option 1, 2, 3, 1, 2, 4 and reach option 3, or you can see that this is very close to Fibonacci. Right? Of course, you can also solve this using extended master's theorem, and you can show that this will be order of 2 power n by 2. You can show that, by the way. You just have to put in your a, b, k, all of that stuff in extended master's theorem. Okay, but by just looking at this 4 functions, I could quickly see that, okay, this cannot be the case, this cannot be the case, this looks very much like Fibonacci, this cannot be the case. You can actually answer this much faster. Of course, you have to be careful. That might sometimes lead you to mistakes. Solving it using extended master's theorem is guaranteed, but it could take a lot of time. Okay, that's all I'm suggesting. And of course, you have to remember extended master's theorem. Okay. So the next question, this is a very good question. So just give me a second before I go into it. I'll just quickly sip a cup of water. Okay, I'll do it. Okay, so I'll just move the screen a little up. Okay, sounds good. Okay, because that's all useless space there. Okay, this question was tricky. So it took me some time to figure. It's not hard, by the way, it's just tricky. So sort all these functions in increasing order of asymptotic growth. Okay, see, we have these three terms. Look at this, all these three terms are all in the form of 4 power something. So if you take log base 4, okay, I'll be comparing n power 4, 4n, and 4 power n. Obviously, it is obvious that 4 power n is greater than everything else. Of course, I'll have to compare these. I'll have to compare these with these other ones also. Okay, I'm not yet resolved there, right? But 4 power n, again, we have solved similar problems, right, in other practice tests. So if I take log base 4 for all these three terms, I would be left with the exponent n power 4, 4n, and 4 power n. Obviously, we know 4 power n grows much faster than any of these two. So 4 power n is the fastest. And unfortunately, that's the option that is there in all 4 options. So you can't eliminate anything with that. Okay. So that's taken care of. Okay. Now let's go to the, okay. So now let's go to the rest of them. Okay. 4 power n is anyway the most, so this is already taken care for. This is the worst. Now let's compare 4 power 4n and 4 power, so obviously 4 power n power 4. Look at this. This is n power 4 and this is 4n. N power 4 is polynomial and this is linear. So 4 power n certainly grows faster than this. Okay. So 4 power n power 4 obviously grows faster. So this is one possibility. This cannot be the possibility because n power 4 grows faster than 4n. So this cannot be the answer. Let's eliminate it. Okay, so this cannot be the answer. Here you have 4 power n power 4 after 4n. Yes, this could be the answer. This also could be the answer, right? And again, this can't be the answer. I'm just eliminating it. Okay, so that is taken care of. Okay, so 4 power, so I've also placed this and this. Now let's look at 4 power n power, sorry, 4 power 4n. So I have 4 power 4n here, which I don't know. I'll have to compare this with these other terms. Here, this looks to be slightly larger, right? So this is certainly larger than this because I have n by 4 power n by 4 here. I have n power n by 4. Obviously, n by 4 is less than n. Your n by 4 and n by 4 are the same here. But the base here of the exponent, which is n by 4, so this is less than this. So this is certainly less than this. So let's compare this with n power n by 4. Let's compare these two. So I'm comparing this with this. Before we compare that, actually we have to compare these two first, right? But I don't have to worry about that option because that option is not there. Okay, but ideally, what should I be doing? Ideally, I should be comparing. Let's just do that, no? Because it's easier. So I need to compare n power n by 4 versus 4 power 4n. Actually, I should be comparing these two also because we don't know which of these two is larger. Okay, so let's compare that. Okay, so this is n power n by 4. So let's take log on both sides. You get n by 4 log n versus 4n log 4. Right? You get 4n log 4. Okay, we are comparing these two, right? Okay, let's compare these two. So the only viable options, so the first option cannot be right. This fourth option cannot be right. So this cannot be right, this cannot be right. One of these two has to be right. Okay, if you compare these two, so I'm comparing n power n by 4 and 4 power 4n. Take log on both sides of any base, doesn't matter, right? So what do I get here? I get n log n with some constant 4 here. What do I get here? I get 4n, log 4 is 2. So I get 8n here, I get n log n here. See, here I have n log n, here I have only n. Log 4 is a constant, right? So obviously this is going to go faster because n log n grows faster than n. So n power n by 4. So the takeaway is n power n by 4 grows faster than 4 power 4n. Right? So we have only two options here. Let's look at which of these two options actually do the justice here. So n power n by 4 grows slower than 4 power 4n. So I think all these options are wrong here. I think there is a mistake with all the options. I'm sorry. I think there is a mistake with all the options. So you can't eliminate. But anyway, let's solve this problem. Okay. Let's anyway solve it. So what do we have? The fastest growing is 4 power n. Let's write it down here. Then I have 4 power n by 4 again. Then I have n power n by 4. Then I would have, again, we'll have to test some of these, right? Oh, actually, I think what we'll have, we can use the similar method. I think all these 4 options are incorrect. Again, we can just use the same method of taking log on both sides and comparing it. I think what we will get here is, this followed by 4 power 4n, and then I think you get n power log n. Okay, let's actually prove this. Okay, let's actually prove that is true. Okay, let me just erase this whole thing. Let me just increase the pen size, the eraser size. Okay, so I think this is the answer. I think all these answers are incorrect, unfortunately. Sorry for that mistake. But let's go one by one, right? So how do we compare these two? Now we have to prove that these two, right? So let's go. So n power n by 4, 4 power n power 4, right? So take log on both sides. What do you get? I get n by 4 log n. Take log on this. What do I get? I get n power 4 log 4, right? So what do I have? I have n log n here. This is constant. Ignore constant. Ignore constant. I have n log n and n power 4. Obviously, n power 4 is larger than n log n. So this is anyway. So this order is right. Till now, order is right. And I know this is less than this. I know that for sure because this is n by 4. This is n. The exponent is the same. So now I have to compare these two. Okay, I need to prove about these two also. Okay, so let's go these two. 4 power 4n, n by power 4, n by 4. So let's take log on both sides again. 4n log 4. What about this? I get n by 4 log n by 4. Right? So log 4 is constant. Just ignore constants here. Ignore this constant. What do I have? I have n here. I have n log n here. Because log n by 4 is log n minus log 4. Log 4 is a constant. Right? So I have n here. I have n log n. So obviously this is greater than this. Now I have to compare these two. Right? So I think, again, let's solve the whole problem anyway, since all the 4 options are incorrect. So let's take log on both sides. What do I get? I get log n log n. This log n comes out log of n, right? And I get 4n log 4 here. Log 4 is a constant, 4 is a constant. We know that log n, what is this? This is log n squared, and this is n. We know log n squared is less than log n, is less than n, sorry. We have seen this in asymptotic growth of functions in many, many examples earlier. So this is the correct order. And how did we discover the correct order? Unfortunately, all these options are incorrect. Sorry for that. I think it's a typing mistake on our side. But this is the right order. And how did we get the right order? Just using simple logarithms and the order of functions that we studied for so long. Right? Very simple problem. Just requires time and patience. That's it. Okay, so let's go to the next problem. Okay, I'll try to cover as many as I can. Whichever we can't cover, we'll send you detailed written answers for them. Just a quick water break again. I'm sorry, apologies today. I'm taking too many water breaks, but I'll keep them short. Okay, now here comes the question. This is actually a very good question. There is a twist here that I'll tell you at the end. Okay, I'll not tell you the twist till the end. So you have 5 sorted sequences of lengths 20, 24, 30, 35, and 50. PQRST. They are to be merged into a single sequence by merging together 2 sequences at a time. The number of comparisons that will be needed in the worst case by the optimal algorithm for doing this, right? So you have 20, 24, 30, 35, and 50. To merge these two, so let's start merging these two, right? How many comparisons do you need? People will obviously say 44, which is incorrect. You only need 43 comparisons. Okay, again, just look at the base case. Imagine I have 2 arrays of 2 elements each. To merge them, the maximum number of comparisons that I would need is only 3 comparisons and not 4 comparisons. It's a very common mistake that people run into and put in wrong answers here. Again, you can test this. You can test whatever is the sequence of numbers here. The maximum number of comparisons that you will need. So you'll compare 1 with 3, right? So 1 will be taken. So you'll have 2 again. That's 1 comparison. Second comparison, 2 and 3. This is done. So with 2 comparisons, you're done here. But in the worst case, you could have 3 comparisons. You will never have 4 comparisons. So let's take this, right? Again, I'm just trying to see. 2 and 3 will be compared. 1 comparison. 2 is sorted out. Then you have 1 and 3. Oh, no. So let's change this. Okay. What if you have 1, 4? Okay. So what if you have 1, 4 and 2, 3? And 2, 3 or 3, 2? 1, 3, 2, 4 actually. Okay. So you'll compare 1 and 2, right? 1 will go away. Then you'll compare 3 and 2, right? 2 will go away. Then you'll compare 3 and 4. The total of 3 comparisons, not 4 comparisons, right? And this is a big mistake that many people run into. And remember, this is a fill in the blank type of question. There are no options here. You make a mistake, you're done. So first we'll merge these two arrays, which require 43 comparisons. So let's keep this 43 here. And the resultant array will be of size 44. So I have now an array of size 44, 30, 35, and 50. Now I'll merge these two. And I'll get an array of size 65. So now I'll have 65, 44, and 50. Now remember that to merge these two, the resultant will be 65, but I would need only 64 comparisons. Next, I'll merge these two, 44 and 50. I would get an array of size 94 from that. But the number of comparisons I need is only 93. Okay, the number of comparisons I need will be only 93. Now I'll merge these two. The final resultant will be 159, but I only need 158 comparisons. What is the total sum of all of these comparisons? It will be 358, which is the answer. Now comes the twist. Why am I picking? Why am I picking P and Q? Let's see, P, Q, R, S, T, right? Why did I merge P and Q in the first iteration? Why did I merge R and S in the second iteration? Why didn't I merge this 44 with 30? Why didn't I do that? Right? Obviously, obvious question, right? I didn't tell you that while I was going. I'll just tell you, okay? In the third iteration, why didn't I merge 44 and 65? Why did I merge the two smallest arrays? See, every time if you notice in each iteration, I'm picking the two smallest arrays and I'm merging them. I'm picking the two smallest arrays and merging them. I'm picking the two smallest arrays and merging them, right? To get 24. And when I have only 2 elements, I'm doing this. This is an example of a class of algorithms called as greedy algorithms. Again, we will learn this later in this course of data structures algorithms, but you can prove mathematically for this problem. You can prove very rigorously that picking the smallest sorted sequences every time is the best way. It will have the least number of comparisons. Again, this has not been covered till now. This has not been covered. We will learn about greedy algorithms later in this course when we learn about graph algorithms and all of that. Okay. When we learn about greedy algorithms, you will be able to appreciate this answer better. So this answer requires knowledge of not just merge sort, but also knowledge of greedy algorithms. But we gave it in advance. Okay. I mean, of course, I don't expect you to know greedy algorithms right away without us covering it. But if you could solve it, very good. You know the basics of greedy algorithms, right? But I also want you to try out in your own spare time. Just try out. What happens if you don't pick up the smallest sorted lists every time? What happens then? Just try it out and see if you can get a number which is less than 358. If you do let us know. Okay, sounds good. Next question is question 20. Oh, sorry. Next question is question 20. Yes. Okay, so what is question 20 now? This is actually a good question. So in question 20, suppose we have, right? Suppose that the splits at every level of quicksort are in proportion 1 minus m and m. So you have a quicksort here. Okay, you're breaking this. This is your pivot. You break it into 2 problems of size 1 minus m into p and m into, sorry, not p, sorry. 1 minus m into n. Sorry. So you're breaking this into 1 minus m into n, and this has m into n, where m lies between 0 and 0.5, and it's a constant. M doesn't change. M is a constant here. So if m is less than equal to 0.5, then obviously 1 minus m is greater than equal to 0.5, right? And 1 minus m is greater than equal to m, right? Obviously, right? So this is where your pivot element is, right? So this is important to realize. Otherwise, you can't solve this problem. The number of elements in the array is n. The maximum depth of this is approximately how much? It's a very good question, actually. Okay, so let's go step by step, right? So the maximum depth. So look at this. I have a problem of size n, which is broken down into a size of 1 minus m into n and m into n. This is less than equal to this, if you look at the size, because we just saw, right, m is less than equal to 1 minus m. So there could be more elements here than here. Or the number of elements here will always be less than equal to this. Now this will again get broken up. This will keep getting broken up. Now if you notice, This path will be the deepest path, right? This path will be the deepest path, and this path will be the shallowest path. Of course, they both can also be equal if m is exactly equal to 0.5, right? But the deepest path, because there are more numbers here, this path could be the deepest path till you reach 1. And what is the depth of this path? Look at this. I keep breaking down this, right? Every time my n becomes 1 minus m into n, which again becomes 1 minus m into n. So on and so forth up to 1. So what is the depth of that? I can easily compute the depth of that as 1 minus m into d, 1 minus m power d into n is equal to 1. When this condition is satisfied, that will be the depth of this path. Look at this depth on this side. If the depth is d, it satisfies this condition. Now, as soon as it satisfies this condition, what can I say? Take log on both sides, right? If I take log on both, see, whenever you see anything in the exponent, you take log. That's it. D log 1 minus m, right? Yes, okay. Plus log n equals to 0. Okay, so if I simplify this, what do I get? I get d equals to minus log n by log 1 minus m. This is the depth that I get. And I have this as option C. My problem is solved. So this is actually a straightforward problem. All you need to understand to solve this problem, this whole m and all of this is just to confuse you. All you have to understand is the maximum depth will occur here because m is less than equal to 1 minus m. That's all. If you know this, because of this property, m will always be less than equal to 1 minus m. And the maximum depth here, again, we have seen these recurrence relations many times, right? We actually discussed this type of recurrence relations a lot. So by now, I want you to be fully comfortable with recurrence trees and all of that stuff. You should be able to solve these problems about recurrence trees even in your sleep. That's how much practice we have had, right? So that's all. Your answer is 3 here. Okay, sounds good. So let's go to 21st problem. We are 2/3 the way. Let's see how many problems we can solve. We'll try to solve as many as we can. Okay, so 1 second. So am I on the 20th problem or the 1 second? Okay, I solved the 20th problem. So let's go to the 21st problem, right? Okay, so for the 21st problem, I want to postpone this problem because there is a lot of recurrence here. There is function call here, and we have not yet discussed call stack. So one other student asked a question, I think in the chat box earlier for this live session. He asked about the space complexity. Of Quicksort. Okay, I intentionally did not explain it right away because when we learn stacks a little later in data structures, I think this week, in the coming week, we'll learn stacks. When I explain you about stacks and push and pop operation, I'll also explain you a lot about call stacks. Call stacks are a brilliant concept in programming, which are used extensively during recursion. So when we understand call stacks, you will be able to understand the space complexity of Quicksort better. Similarly, this problem can be better solved when you understand the call stack. I don't want to jump to it right away. So once we learn about stacks, we learn about call stacks in a lot of detail and how programming languages use call stacks for recursion. What is the problem? Is there a mistake? Option D, minus log n log 1 minus m. Oh, sorry. It's sorry. It's log 1. What did the answer did I say? What answer did I say? Sorry. It's option D. So sorry. My bad, guys. Actually, the answer that we got here is Let's see. What we got is log n by log 1 minus m. Okay. Sorry, I didn't see this clearly. It's not C. It is D. I'm sorry. Thank you for the correction. Yes, it is D. I didn't see this. My mistake. Thank you for the correction, folks. Thank you. Yeah, see, silly mistakes again. Anyway, yeah, we all get into that trouble. Okay, thank you, folks. Thank you for the correction again. Again, if I make any mistake, do let me know. So we will move this problem at the end of stacks when we learn call stacks and solve it much better once we understand it, right? So next comes question 22. Okay, what is question 22? Okay, let me see. Okay. This is a terrific question. Okay, let me just zoom this out a little. This is a terrific question. I think this is a gate question. Which year is it? 2007. Oh, again, the same year that I'm sure I couldn't have solved this when I was preparing for Gate. Again, this is the year that I wrote Gate. I wrote Gate in 2006 and 2007. I'm sure I couldn't have solved this because this is a very tricky problem, but a very interesting problem. So it will take us some time to solve it, but let's go ahead with it, right? The question here is the GCD of two numbers is the largest number that divides both of them. We all learned about GCD when we were in school, right? Below is the recursive function to evaluate GCD using Euclid's algorithm. Okay, what does it say? It says if n percentage m equals to 0, return m, or else n equals to n percentile m, return GCD m comma n. Okay, very simple recursion, looks very simple. How many recursive calls are made by this function in the worst case? Again, I think the question needs to be changed slightly. How many recursive calls are made by this function in the worst case? Because in the best case, imagine if I give GCD of 2, 4. There is zero recursive calls made, right? In the best case. Because 4%, sorry, 4, 2. I should give 4, 2. Because 4 percentile 2 will be 0, return 0. Sorry, return 2. Problem solved, right? In this case, 4 percentile 2 equals to 0, so return 2. So no recursive calls are made. But the problem becomes fun when you see how many recursive calls are made by this function in the worst case. This requires you to know a very interesting property of GCD. Again, I'll come to it. It's a big surprise. It's a very important property of Fibonacci numbers. It's a very important property of your Fibonacci numbers. The worst case, I think the question could have been slightly modified for the worst case. The worst case of this happens if your n and m are consecutive Fibonacci numbers. This is one of the big things that you need to know to be able to answer this question, unfortunately. Okay, if you don't know this property, that Fibonacci numbers are the worst case scenario for Euclid's algorithm. Solving this will be hard. Okay, and frankly speaking, if somebody did not tell me that, I wouldn't have been able to figure it out in an examination setting, right? Probably not, certainly not in a gate exam. I'm sure I couldn't have solved this in 2007 when I wrote the gate exam. So this is a tricky question, and it requires you to know this very interesting property that Euclid's algorithm, which is given here, worst case happens when you have two consecutive Fibonacci numbers. Let's take an example, right? Let's take n equals to 34 and m equals to 21. These are two consecutive Fibonacci numbers. Let's see what happens. You call GCD with n equals to 34, m equals to 21, right? So now just compute this, right? So it will again call GCD with what will be the values when it calls again? It calls with 21. It calls with 21 and n percentile m, 34 percentile 21. What will be the 34 percentile 31? 13. So it will call the function. It will call the function with 21 and 13. Right? Next thing. In the third iteration, what will happen now? It will call with 13 and what is the difference between both of them? Remember, they're Fibonacci numbers. The difference between both of them is going to be 8. In the fourth call, you will get 8, 5. In the fifth call, you will get 5, 3. In the sixth call, you will get 3, 2. In the sixth call, you will get 2, 1. And 2, 1 is where it will finish. Right? So when I called again, remember, I think okay, there has to be one more. I think there is one more thing missing here. I think one thing that is missing here is n is greater than m. I think this should be given here. Okay, is it given somewhere? I think that is missing. Okay. Oh no, it's given here. Okay, let n be greater than m. Okay, this is important. Okay, otherwise I can't do this. That's what. While solving this, I realized that n has to be greater than m for me to work this out. Again, folks, it's very important to realize that if you don't know that the worst case of Euclid's algorithm happens when you have two consecutive Fibonacci numbers, figuring it out in an examination setting would be impossible. Trust me. Okay. So I think this is there in CLRS somewhere. I remember reading it in my during my master's at Indian Institute of Science. I remember reading it. Again, it took me a while I actually forgot that. And one of our teammates actually helped me with this problem. I couldn't solve it without knowing this fact, to be honest. Okay, so since we know this now, let's see. So now when I start with n, what is the depth of my recursive tree? I called this algorithm. I made recursive call 7 times. Can you get a bound on this? Now there is one more property of Fibonacci numbers called the golden ratio. Okay, called the golden ratio. I think it was Fibonacci himself. Fibonacci is an Italian mathematician, if I'm not wrong. It was people like Fibonacci and the great what is this guy's name? The great painter, the great Italian painter, Da Vinci, who discovered patterns called golden ratio in nature, right? So one of the interesting properties of golden ratios is that every pair of, so if you look at any two numbers, any two consecutive numbers, any two consecutive Fibonacci numbers, like any two consecutive Fibonacci numbers, they would have a ratio of approximately 1.618. This is called the golden ratio. It occurs so many times in nature that you'll be surprised by it. And that's why Fibonacci in the first place was interested in these numbers, because the ratio of these numbers were converging to golden ratio as the numbers increase. Okay, I mean, that's why, again, remember, this was a time of Renaissance in Italy, when some of the greatest artists, mathematicians, philosophers, thinkers were finding patterns in nature, right? So Fibonacci was one of those guys, and he found this brilliant system. I think there is also a story of Fibonacci finding the sequence while mating rabbits. So he would have one rabbit or two rabbits, and then they would mate into two. There is some exercise like that. I remember reading it on Wikipedia a few years back. But anyway, coming back to our discussion here, if I have 34 here, one thing that you'll notice quickly is so initially my problem is of size 34, right? 2 steps later, look at this, from 34, my n was 34 initially. From 34, I went to 21. And this ratio is roughly 1.618. And this ratio is roughly 1.618. This ratio is roughly 1.618. This ratio is 1.618. So my n, if you think about it, if my n is some number, the next value of n that I get is roughly the golden ratio into n. Then the golden ratio square into n, right? So a problem of size n was getting decomposed into a problem of size golden ratio into n, right? Again, in the next iteration, golden ratio square into n, golden ratio cube into n, right? And so on and so forth. Now, what will be the depth of, see, the depth of this tree is the number of recursive calls you make. So the moment you see a pattern like this, you should quickly say, yes, this is basically log n, of course, base 1.618, right? So this is the depth of the tree, right? So if this is the depth of the tree, which of these 4 is the most appropriate? Obviously log n, right? Again, to solve this problem, you have to know 2 very important factors. Number 1 is the worst case of Euclid's algorithm happens when you have consecutive numbers and the golden ratio. You have to know both these facts. Without them, solving this question is impossible. I'm very surprised that somebody asked this question in Gate. I am sure there would have been less than, I don't know how many people actually solved this problem in Gate. Because, I mean, I am sure I wouldn't have solved it. Okay, this is a very hard problem where you require a lot of knowledge about number theory and about Fibonacci numbers. Without having that historical and number theoretic perspective, solving this is like almost impossible. Okay, so, but this is a hard question, but a very good question. Of course, without these 2 points, I think nobody can solve unless you're a genius. Okay, so let's go to 23rd problem. Oh, sorry, let's go to the 23rd problem. Okay, so what is the 23rd problem that we have now? An array of n numbers is given where n is an even number. Okay, very good. The maximum as well as the minimum of these n numbers need to be determined. Which of the following is true about comparisons? We actually solved a very similar problem in the previous practice problem, right? Where we had 100 numbers, right? We had to find the minimum and the maximum in this, right? So just going by the same logic. Sorry, just give me a second, folks. Okay. So just going by the same logic, we've solved a very similar problem. Here, instead of 100, you're given an n, which is an even number. So first I'll take the first 2 numbers. I'll see which number is the larger. Let's assume A1 is larger than this. I'll make min equals to A2 and max equals to A1. I'll initialize min and max. So how many comparisons did I make here? I made 1 comparison here, We've seen this similar problem. Then I'll take A3, A4. I'll take two numbers. First, I'll determine if A3 is greater than A4. Let's assume A3 is greater than A4. So one more comparison made, right? Now, if A3 is greater than A4, I'll compare max with A3. So that if A3 is greater than max, I'll change my max. So this is one more comparison. And I'll also compare min with A4. If A4 is less than min, I'll make min equals to A4. So how many comparisons did I make? 1, 2, 3. So total of 3 comparisons. So for every pair of numbers from here, okay, up to an-1 and an, I'll make 3 comparisons, right? So for all of these n-2 numbers, right, I'll have 3 by 2, 3, 3, 3, 3, etc. Right? So sorry, how many pairs do I have? Sorry, let's see. How many pairs do I have? See, look at this. If I do A3, A4 here, next I'll take A5, A6, right? So there are total of n by 2 numbers here. Sorry, n-2 numbers. There are total of n-2 numbers because first 2 numbers are already taken up. The n-2 numbers, right? And for every pair of numbers, I have 3 comparisons, right? Which means the total number of comparisons will be 3 by 2 into n-2, right? Plus 1 because of this one, right? Now let's solve this, okay? 1 plus 3n by 2 minus 3. So this will be 3n minus 2 minus 2. Okay, this is nothing but 1 minus n minus 2 comparisons are needed. Right? Obviously, at most these many comparisons are needed to find out the min and max. The only difference between this problem and a similar problem that we solved, I think, in the last practice test is, again, remember, n is an even number here. That's why this whole thing worked for me. Right? Otherwise, that's why 3n by 2 works out. Otherwise, you'll have to change the formula slightly. Right? So, yeah, otherwise, I think you'll have to just make it 3 by 2 n minus 1, I think. Anyway, just check that out. Okay. Okay, so 23rd is also done. Let's try and tackle 24th. Okay, I'll solve a few problems here. I'll solve the easier ones. Okay, so that we are here. I think this is a very straightforward problem, if I recall. The given array is divided such that instead of dividing the array into 2 halves, it gets divided into 3 parts, such that one part consists of 10% of elements, second part 40%, and the third part consists of 50% of elements. Rest of the procedure remains the same as in standard merge sort. Which of the following reconciliations belongs to the version of merge sort? Obvious. Look at this. I mean, I can literally glance and say, okay, this is 10%, this is 40%, and this is 50%. That's it. Option A. While the question is large, the answer is trivial. There is no reason why I should get this. I should not get 25%. I should not get 25% because I have 10, 40, and 50. That's it. Problem solved. This is like a 30-second question if you can read fast. Okay, so let's go to the 25th question. Oh, this is a good question actually. Okay, so given a set of n distinct numbers, right? Given a set of n distinct numbers, we would like to determine the smallest 3 numbers in the set using comparisons. Remember the smallest 3 numbers. Okay, this is actually tricky. Which of the following statements is true? Okay, so okay, these 3 elements can be determined in log n square comparisons. Anyway, let's see the problem. Let's say I pick every pair of elements like this. Okay, I compare every pair of elements, right? To determine which of them is smaller. First, let's find the smallest elements first. The smallest element, let's find it first. How many comparisons do I have to make here? I have to make n by 2 comparisons here in the first iteration. Then how many elements do I have now? I have n by 2 elements. Now I'll keep comparing them. Think of it like a tree, right? Now how many comparisons will I make at this level? I'll make n by 4 comparisons. I'll keep doing it. Like I'll have n by 8 elements now. Now I'll compare n by 8 elements. See, every time you're reducing it up to 1 element. So what I'll do here is, imagine if I have 2 and 3 here, I'll pick the smaller element here. Okay, if I have, let's say, 4 and 6 here, I'll place the smaller element here. Basically, I'm constructing the comparison tree. Basically, what am I doing here? I'm constructing the comparison tree here, right? That's what I'm doing literally. Now, what is the depth of this tree? The depth of the tree is log n. So I can get the smallest, the depth of the tree is log n. But how many comparisons do I have to make? In the first iteration, I made n by 2 comparisons. In the second iteration, I made n by 4. Third iteration, I made n by 8, so on and so forth up to 1. This is basically a geometric progression. We have solved this many times, right? So this is obviously order of n log n, right? So this is sorry, this is order of n. I'm sorry, this is order of n. I'm sorry. My bad, folks. So this is basically, if you remove n, you get half plus 1/4 plus 1/8 plus so on and so forth, and this sum is equal to 1. So this is basically theta of n, right? So let's keep theta of n. So to compute the smallest element, it took me theta of n using this recurrence. Then you might wonder, why the heck did you waste your time doing all of this, right? If it's anyway taking you n comparisons, why did you bother about all of them? It's actually not theta of n, it's exactly equal to n. It's actually exactly equal to n, right? To find the smallest element, it's actually exactly equal to, I think, n or n minus 1. I think it will be exactly equal to n, right? So now what you get here is, look at the options. It's order of log n square. Obviously, this cannot be the case. Order of log n square comparisons do not suffice. However, these three elements can be determined in n plus order of 1 comparisons. We already got n. Okay, so can we, given the smallest element in n comparisons, can we find the second and third smallest in constant time? Let's see. The third option is n plus order of 1 comparisons do not suffice. However, these three elements can be determined in n plus some theta of log n. Okay, theta of log n comparisons do not suffice. However, these three elements can be determined in order. See, this is trivial, right? In order of n comparisons, it's trivial. I basically create three A, B, C. Okay, if it's order of n comparisons, it's very simple, right? I don't have to do all of this tree structure, but I have to test that it is not possible here. Certainly, it is possible in order of n comparisons. I'll just create three variables. In this variable, I'll always store the smallest element, the second smallest element, and the third smallest element. Solving this in order of n time is trivial. The challenge here is, can you do it in n plus big O of log n? That's the question. So let's go back. So this is known. If you cannot do it in this time, then obviously 4 has to be the answer, right? First, let's see this. So we already got the smallest element, and look at this tree. What did I do? Every time I picked up so look at this. So I have 4 here, 2 here. So I would pick 2 here, right? Every time, look at this. Every time I picked up the smallest elements to come to the smallest element at the bottom. Now, because this is the smallest element, I can go back this tree because I've already constructed this tree. I've already constructed this comparison tree here. Now, where will the second element lie? If you think about it, the second smallest element could lie here. See, imagine, look at the path through which I got the smallest element. Let's assume the smallest element is 2. Look at the path that the smallest element has taken, right? The second smallest element has to be on the right side, on the compare, because if this is the smallest element, it always 1 against some other element. You can actually prove rigorously that the second smallest element had to be in this area, right? Had to be on the right parent. Again, we have not covered trees right now, but when we cover trees, you'll learn this better, that it has to be this, or everything that 2 got compared with. And what is the depth of this tree? How many such nodes exist? The depth of the tree is only log n. So you can compute the second smallest element in log n time. Once you get the second smallest element, you can also compute this third smallest in log n time. Which means, because all this is possible because while computing the smallest element, we built this whole comparison tree. Without building the comparison tree, if I just used 3 variables, this would have been impossible, right? Because I have this comparison tree, because there's a lot of structure here, I'm just leveraging this structure to find the second and third smallest elements, which could be found in order of log n, because the depth of this tree is log n. Again, you will understand some of these things better when we learn binary search, right? And trees in general. We'll learn about binary search trees and things like that little later. So, but the core idea here itself is simple. Just in the interest of time, because it's a Saturday evening, I don't want to eat up everyone's time. So we have solved 25 questions. We will share the answers to all these questions, all the 30 questions. For 26 to 30, some of them are easy, actually. Most of these questions are easy. The harder ones have, I think, have all been covered. But we'll share written answers to all of them, especially for 26 to 30. If you have any questions for all the registered students, please revert back to us. We will do everything to resolve your questions. And please note that this session was one of the harder sessions in terms of questions. We just want you to be prepared for the worst case. There is nothing wrong with preparing for the worst case. You will be better off, trust me. Happy weekend, enjoy yourself. By tomorrow morning, we'll send the schedule for our next session on Wednesday. Right? We have the next session on Wednesday evening, same hours, 7 to 8:30 p.m. We're already overshot by a while now, but we will conduct it on Wednesday. We'll also send the schedule in, and let's try to finish whole of data structures algorithms by the last week or by end of March. Okay, folks, thank you for joining us today, and yeah, thank you for being patient through a very long session. Thank you, folks. See you then.